Hello guys, welcome back to another video on my channel. So far we've done integrals for quite a long time. I thought to myself, it's definitely time for an infinite sum. In this case, well, it is a product. So with that being said, let's get started. So this problem is actually from the Berkeley Mathematics Tournament for the year 2021. And it goes as follows. Let P equal the infinite product from n equals 1 to infinity, pi times arctangent of n over 2 arctan of 2n times arctan of 2n minus 1. Now before we proceed, actually, let's do a limiting approximation of P, which we usually do for such kinds of problems. So define the nth partial sum, Pn, so that when we take the limit as n goes to infinity of Pn, we actually get the original infinite product. So in this case, it's less a partial sum, more a partial product. Pn equals product from n equals 1 to capital N, pi arctan of n over 2 arctan 2n arctan 2n minus 1. Now, we have too many products and quotients. It will be easier to use the properties of the natural log. So we take the natural log on both sides. Natural log of Pn equals natural log of the entire quantity. Now, one of the wonderful properties of the natural log is that a product becomes a sum. So a product inside the natural log becomes a sum of natural log. So that when you take essentially the product outside, it becomes a sum. So sum from n equals 1 to capital N, ln of this giant quantity. But another property of the natural log is we can decompose this completely. So each product inside the argument of the natural log will be a sum of natural logs, and the quotient will be a subtraction. So from the pi and 2, we have sum from 1 to capital N, ln of pi over 2, plus the term in the numerator, sum from n equals 1 to capital N, ln arctan of small n, minus the term in the denominator. We accounted for the 2, so we have 2 remaining arctans we have to write down. So sum from 1 to capital N, ln arctan of 2n, minus, because even this was in the denominator, sum from 1 to capital N, ln arctan of 2n minus 1. Okay. How does this help us? Well, we can simplify these last two terms of arctan. So you have both of them. There's sum from 1 to n. One is ln arctan of 2n, the other is ln arctan of 2n minus 1. So if you actually write down each individual term in the sum, so when you say small n equals 1, we have ln arctan of 1 and ln arctan of 2. Similarly for 2, we have ln arctan of 3, ln arctan of 4, so on, until we reach n, when we have ln arctan of 2n minus 1 and ln arctan of 2n. So that means we're basically summing over all possible values of n from 1 to 2n of ln arctan. And that's what happens when we combine both of these finite sums from 1 to n, is we get a big sum from 1 to 2 capital N of ln arctan of small n. Okay, so that means these two difference terms can be written as one term. Meanwhile, ln of pi over 2 is a constant with respect to small n. It can be pulled out, and then we just sum n from, we sum 1 from n equals 1 to n. So we sum 1 n times, so we get a factor of n. So we have that factor of n times ln pi over 2. The first ln arctan term remains, and we combine the last two to sum from 1 to 2n of ln arctan of small n. And now we can actually combine the last two terms again. We have sum from n equals 1 to 2n, and we're taking a difference, again with a minus sign, from a sum from 1 to n. So 1 to n is a smaller sum than 1 to 2n. So that's like removing the first n terms from the sum from 1 to 2n. So that means we are left with sum from n plus 1 to 2n, because the first n terms got removed, of ln arctan of small n. The first term of n ln pi over 2 is the same. We're actually not quite done with the problem. You might notice immediately that we cannot take the limit here, because if we try to take a limit as n goes to infinity to recover our p, we have an n up front, so the first term will diverge, and we don't know anything about this series. It looks quite complicated as a series. So what we'll try to do is, well, we can't simplify the first term any further. We'll try to simplify or try to approximate uh, the ln arctan for large n. Why large n? Because we're summing from capital N plus 1 to 2 times capital N, and n will be taken to go to infinity. So whatever approximation we have, we can take it under the assumption that the argument is large, in this case, which is n. So let's first use the identity arctan of x plus arctan of 1 over x equals pi over 2 for x greater than 0. So then notice that as x goes to infinity, then 1 over x goes to 0. And when things go to 0, the Taylor series becomes easier to manage. And that's exactly what we'll do. We'll write arctan of k as pi over 2 minus arctan of 1 over k, and then use the Taylor series around the point 0. So arctan Taylor series around 0 is arctan of z equals z minus z cube over 3 and dot 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 higher order terms. So using the pi over 2 minus arctan 1 over k, and then writing the arctan 1 over k using the Taylor series, we get that arctan of k is pi over 2 from before minus the Taylor series, which is 1 over k minus 1 over 3 k cubed, because z was 1 over k. So that just gets cubed, and so on. We can write this using the big O notation. So pi over 2 minus 1 over k plus order 1 over k cubed, because all the terms that follow in this series will have higher and higher powers of k in the denominator. So that means they're going to be progressively smaller terms. And we can just represent all those ordered terms by writing O of 1 over k cubed. So which denotes that all the terms are at least of order 1 over k cubed. And now arctan of k really wasn't the summand we had. We had ln of arctan. So that means we have to take the natural log. So natural log arctan of k with the approximation we have before is ln of pi over 2 minus 1 over k plus big O of 1 over k cubed. We can pull out a pi over 2 factor. Ln of pi over 2 times 1 minus 2 over pi k plus big O of 1 over k cubed. And again, the big O doesn't care about any of the factors. All it cares about is the effective power, which is in this case k, the variable power. We can use the property of the log. If you have a product in the arguments, you can write it as a sum of a natural logs. So natural log pi over 2 plus the rest of it, natural log of the rest of it. So 1 minus 2 over pi k plus big O 1 over k cubed. We can simplify the second term even further. We will use the Taylor series for ln of 1 plus u, which is given by u minus u squared over 2 dot dot dot. When we do that, so ln pi over 2 is unchanged. We will have, instead of u, we have this term of negative 2 over pi k plus big O of 1 over k cubed. So That's u. So when we write that, we have negative 2 over pi k, and the next order term, which will be of the highest power, or the lowest power of k in the denominator, will be the square of this term, because we had a u squared. So there will be a term which has 2 over pi k the whole squared in it, which will be a k squared order term. Everything after that will be order k cubed and higher terms, higher powers of k. Because remember, you also had the big O of 1 over k cubed in it. So the next term that comes from the big O will be a 1 over k cubed term. And again, higher powers of k after that. So the next smallest power of k is a big O of 1 over k squared, which comes from squaring the 2 over pi term. So that's how you see the usefulness of the big O is we can actually keep track of what the smallest power of k, or the biggest term is. So then we have ln of pn is n times ln pi over 2 minus, remember we had a sum in front of that summand, so sum from n plus 1 to 2n of ln pi over 2 minus 2 over pi n plus big O 1 over n squared. So we have the first term as it is, n ln pi over 2. The second term, well, see that it's a constant with respect to small n, so that can be pulled out, and we're summing 1 n plus from n plus 1 to 2n, which is n terms. So we're summing 1 n times, we get a factor of n. So we get n ln pi over 2. The minus and minus will give us a plus. 2 over pi can be pulled out of the sum from n plus 1 to 2n of 1 over small n, and the big O summation. So minus sum from n plus 1 to 2n of big O of 1 over n squared. So notice, to our joy, the seemingly divergent terms which had the n up front, which kind of discouraged us from taking the limit, will cancel out nicely. So we're just left with the last two terms, which is 2 over pi, sum from n plus 1 to 2n of 1 over small n, plus Rn, where Rn is just that last term. So Rn is just minus sum from capital N plus 1 to 2 times capital N, big O of 1 over n squared. And we notice that because the sum from 1 to infinity of 1 over n to the p for p greater than 1 converges, this is called the p series convergence. You can connect this to the Riemann zeta very easily. This is the Riemann zeta of p. And it converges for p greater than 1. So whenever you have such a convergent series, then the tail of that series, and what I mean by tail is um, as n goes to infinity, the last few terms which depend on that limiting variable, which is in this case is capital N, these are the last bits of the term. Those will go to 0. There's a nice result from analysis, which I'm not going to prove here. It is intuitive because the entire sum converges to a value. So the last bits of the sum in the limit as n goes to 0 should vanish as we get closer and closer to the limit value, or the value of the sum. So our n goes to 0 as n goes to infinity. And we can take the limit at this point. So limit as capital N goes to infinity of ln of Pn is just ln of P, because we can take the limit inside the natural log. The natural log is continuous. So that means the only term that remains in the limiting process is the one that's not Rn, because Rn vanishes, remember? So we have limit as capital N goes to infinity of 2 over pi, sum from capital N plus 1 to 2 times capital N, 1 over small n. We can break this up into the difference of two sums. So we have 2 over pi limit and capital N goes to infinity. So we'll have one sum going from 1 to 2n of 1 over n, minus sum going from 1 to capital N of 1 over n. Because sum from n plus 1 to 2n was just take the entire sum and remove the first n terms. That's all I'm saying here. Why is this useful? Because recall the definition of the Euler-Mascheroni constant. Gamma was limit as n goes to infinity of the nth harmonic number, so sum from 1 to capital N of 1 over n, minus ln of capital N. We can rearrange this to get limit as n goes to infinity of sum from 1 to capital N of 1 over n is equal to Euler-Mascheroni plus limit as n goes to infinity ln of capital N. We have a similar kind of expression for the 2n. So if we replace the capital N of the sum by 2n, we'll have to replace this n by a 2n as well. And so we just substitute those in here. So we have 2 over pi Euler-Mascheroni plus limit as capital N goes to infinity ln 2n minus Euler-Mascheroni minus limit n goes to infinity of ln of capital N. You see that the Euler-Mascheronis will cancel. So we're left with a difference of natural logs. So limit n goes to infinity of ln 2n minus ln n. When you have a difference of natural logs, is the natural log of the quotient of their argument. So we have natural log 2n over n, which is natural log 2. And that's a constant as in the limit as n goes to infinity. So it will remain that value in the entire limit. So we have 2 over pi ln 2. Now we have ln p equals 2 over pi ln 2. To reverse, to get 2p, because that's p was the original product that we were given, we can take the anti-log or the exponential. So with respect to e, well, e to the power. So p is exponential of ln of p, which is exponential 2 over pi ln 2. We can 2 over pi ln 2 is ln of 2 to the 2 over pi, and exponential of ln will cancel out, being natural inverses. So we have 2 to the 2 over pi. And that is indeed the final answer for this problem. I hope you like this this video. I know I was rushing through some steps here, like this convergence. All I'll reiterate about this is big O of n has terms which are of order n squared and have higher powers of n. So which fit this criteria of p greater than 1. So 1 over n squared, 1 over n cubed, n fourth, n fifth, all the way for arbitrary power of n, they all converge. And for that reason only, and that reason alone, can we conclude that as n goes to infinity, the tail of that series, of that sum, goes to 0. Because if we did not have convergence, this our n going to 0 as n goes to infinity would not be true. Which is precisely the problem we have when we, before we try to approximate. Remember, we have this sum, and no, first of all, we're discouraged from taking the limit because of this capital N up front on the first term, but also because we cannot argue that this second sum goes to 0 because we do not know whether it converges. And in fact, it doesn't converge. It can't converge because if it did converge, it would go to 0 and we'd have a naked n up front, which would make the entire ln of pn diverge as n goes to infinity. So in fact, this does not converge, and which is why we don't take the limit here, and therefore it does not go to 0. So convergence is important for the tail to go to 0. And that's why this step of approximation was necessary to cancel out the divergence and basically reach the convergent part of this problem. That's it for this video. Please like and subscribe to my channel and recommend me to your friends. Stay tuned for more content, and peace out.